good afternoon. Thank you for joining for our webinar today from Solve. So today the webinar it's under the Team 7, and this is on PV sustainability, and the topic will be on life cycle assessment and also on recycling and end of life of PV panels. And today we are going to be two moderators, myself from Dalarna University in Sweden, and then Michiel van Noord from RISE. To give you a bit of the background before starting, let me see. Sorry. I'm not changing the slides. Okay. So this webinar will be recorded, so just for you to know. And then we'll tell you where is available the recording. So Solve, it's the Solar Electricity Research Center here in Sweden. It comprises 6 institutions, 5 universities, and the research institutes of Sweden. There are many companies that are part of this research center, and we have different projects. We have PhD students and postdocs, and we are, and this is a 5-year project that will probably apply for renewal in the future. This is sponsored mainly by the Energy Agency, the Swedish Energy Agency, by the universities, and by the stakeholders. There are 7 research teams under the Solve. We have the first team that is on advanced PV technology. Then we have building integration and PV systems, land sharing, economics, and business models, planning for large-scale expansion. And today, the team that is organizing this webinar is Team 7 that is on sustainability. On Team 7, it's myself and Michiel that we are heading the team. And then we have also Ihoume that is also from the Dalarna University that is a postdoc in this team. One important aspect is that we Solve, through me and Michiel, are also involved on Task 12 from the International Energy Agency, and some of the guests today are part of that Task 12. Burçak Ebin from Chalmers is also part of Task 12 and is going to present today on the recycling part. But we are also going to have Sebastian Nold that is also from this Task 12. So there will be people from Solve, people from Task 12, and we are going to, of course, to have a guest also from Norway, Rune Søndenå. Now, the agenda is we are going to have, I'm going to be hosting the first 2 speakers, and then we have a short coffee break. And then Michiel is going to take over after the coffee break. In the end, so the idea is to have first discussions, and in the end, we are going to have a roundtable with all the presenters where you can make some questions. So try to save the questions for the roundtable discussion, since we are not going to have much time between presentations. But we'll have at least 30 minutes in the end for discussion about different thematics. Yeah. So, and yeah, if you have any questions about Solve and about our Team 7 or Task 12, you can contact either me or Michiel, and we'll be happy to provide you more information on it. So, our first speaker, and I'm going to remove this part. I will stop sharing. Our first speaker will be Ilham. She's a postdoc here at Dalarna University, but also part of Solve. She did her PhD in Morocco at the Mohammed V University with a focus on renewable energies and environment. And she's with us at Solve for the last 5 months, so she's very new. She's joined us very recently. And she will give an introduction about the activities of LCA we are doing here and what are our plans for the future. Ilham, maybe you can share the slides.
Yeah, thank you for the introduction. So let me share my screen. Okay. So good afternoon, everyone. My name is Ihoume, postdoc at Dalarna University, and part of Team 7 in Solvay project. In this webinar, I will present an overview of LCA and how we use it to evaluate the environmental impact of photovoltaic systems. I'll also share insights from our research, where we are working to improve LCA methods for solar technologies, especially for photovoltaic systems in the built environment. So, as many of you know, sustainability is meeting today's needs without harming future generations. For PV systems, this means designing and using them in ways that minimize environmental impact. The goal is to make PV system eco-friendly, energy efficient, and durable. To do this, we use LCA to measure and reduce their impact. So, what is the LCA? So, LCA, life cycle assessment or life cycle analysis, is a methodology that we use to measure the environmental impacts of a product or a system throughout its entire life cycle. For PV systems, this means analyzing every stage, mining materials, manufacture panels, installation use, and finally recycling or disposal. And LCA, setting the right boundaries is essential, as it shapes the scope of the study. For example, gate-to-gate focuses just on a specific stage like manufacturing. Cradle-to-gate stops at the factory gate, so it doesn't include the use phase or disposal. And we have also cradle-to-grave that covers everything from raw materials all the way to disposal. And finally, we have the cradle-to-cradle, which looks at circular design, where materials are reused or recycled instead of ending up in landfill. So each boundary gives us different insights depending on the goal of the study. The LCA process has 4 main steps, standardized by ISO 14040 and 14044. So first, we define the goal and scope, what we want to study, how we will do it, and what we will include. Then, we move to the inventory analysis, where we collect data on materials, energy use, emissions, and waste. Next is the impact assessment, where we translate that data into environmental impacts. And finally, we interpret the results to understand what matters most and where can we make improvements. Now let's move to the current research at Dalarna University. So within Solvay and the International Energy Agency Task 12, we are focused on developing transparent LCA methodologies, especially for PV systems in the built environment, such as BIPV, Building Integrated, and BAPV, which is the Building Applied. Actually, the reason why we are focused in the built environment is because they represent an important market in Sweden, not only for the PV sector, but also for the construction sector, which is one of the country's largest economic sectors. And also, BIPV are more complex than regular solar panels, as they don't just generate electricity, but also they are part of the building itself. So to achieve this, first we need to answer and understand these 2 questions. Why do LCA methodologies vary so much? And also, why isn't there a unified approach? So to answer to these 2 questions, we started by a literature review where we analyzed the PV LCA studies across the 5 continents. So let's take a look at this comparison between solar deployment and research activities by region. On the left, the map shows the global installed solar capacity. The darker red indicate that there is higher capacity. And on the right, we have the map that illustrates the distribution of PV LCA studies, which dark blue indicates a higher number of publications. We can observe some alignments between, for example, regions with higher solar capacity and those with more LCA research, especially in Asia and the United States. And to make it more clear, I've translated this data into percentage using a tree map in the next slide. So for the solar capacity on the left, we see that Asia dominates with over of 61% of the total capacity, led by China. Europe follows with 20%, America with 15%, and Africa hold less than 1%. This isn't just about geography. It reflects underinvestment in high origins regions like Africa, where infrastructure and support are still limited. In terms of PV LCE research, Europe leads with nearly 47% of all PV LCA studies, driven by strong policies like the waste electrical and electronic equipments and also eco-design directives. Asia, despite its leadership in solar capacity, accounts for under 30% of studies. The Americas are more balanced, while Africa remains underrepresented in both deployment and research. So this mismatch highlights key global gaps, which I'll explore on the next slide. So back to the question, why LCA methodologies for PV system differ so widely? First, we have varied data for each stage. If we take, for example, where materials are mined, how they are manufactured, transported, and even how much sunlight they get, all of this change the environmental result. Second, we have different calculation methods. For example, if we look to the same category like global climate change, there are different methods such as recipe, CML, or Tracy, which translate emissions into potential warming effects, but they use different assumptions, so the results can vary. And third, we have the system. What exactly is included in the LCA? Just the panel itself or also the balance of system? Because different studies make different choices leading to different results. And finally, we have the assumptions and scenarios, because LCA often involves making assumptions about things like the panel's lifetime, degradation rates, and the efficiency of recycling technologies. So these assumptions can vary between studies and influence the results. And why we don't have one global method for LCA of PV systems? Actually, the context really matter, because a PV system made in China, used in Sweden, and recycled in Germany will have a very different profile than one made and used in India. And we also face data gaps, especially for end of life, and also the rapidly evolved technologies. Then there is a legal side, which is really affect the LCA. As we saw before in the plot, strong regulations makes Europe to be much more active in the PV LCA research, but also stakeholders are important, because depending on who's asking, is it industry, policymakers, or researchers, and then the focus of the LCA can change. To better understand how these challenges play out in real life, we decided to look closer to home at our own university. So we launched a pilot study using our campus as a living lab, where we are studying 52 kilowatt VIPV system made of 581 cadmium telluride module installed on our building facade. The goal of this study is to bridge the gap between how construction engineers and PV specialists approach the LCA. For instance, in construction, PV is treated like any other building materials, focusing just on embedded carbon and structure. But in a PV engineer, the focus is on energy generation and also avoided emissions. So they don't consider how the system fits into the building. That's why we are working together with construction researchers, and also we have a master thesis dedicated to this work. To wrap up, LCA gives us a full picture of PV system sustainability. However, for it to be truly effective, we need better data, clear system boundaries, and also methods that reflect real-world diversity. In Solvay, our research aims to address these challenges through case studies and collaborations. But the question that I want to discuss actually in the roundtable is, do we need a perfect, detailed LCA that capture every aspect and represent truly the system, but it's hard to compare? Or we aim just for a simple shared method that different sectors can use? For BIPV especially, I think that it's not just about technology, it's about teamwork. So the solar and construction sector need to sit together and agree. What are the most important questions we need LCA to answer? Because in the end, the key challenge isn't doing LCA, it's deciding how to do it. And thank you for your attention. I try to be quick because we have just 10 minutes. Your voice is muted. Yours, André. We can hear you.
Thank you.
Yeah.
Thank you. You are really on time. Thank you. Yeah, we will have questions in the end that Michiel will conduct this roundtable.
Okay.
So I think those questions I will ask the people that are participating to take notes and maybe comment at the end of the session. And now I'm going to move to our next guest, that is Sebastian Nold, that is from Fraunhofer in Germany, and is also a member of Task 12. And he did his PhD at the University of Freiburg and on techno-economic assessment of new silicon solar cell production technologies. So I think that Sebastian can give us a good insight on LCA, but also as a close relationship with the technology development. So I think will be a very interesting presentation. So Sebastian, the floor is yours. Please take over.
Thank you very much, André, for introducing me nicely and for inviting me to this webinar. Hello, everyone. I'm happy to give you an overview on the bottom-up modeling and life cycle assessment and key influencing parameter of the CO2 footprint, which I'll give you an overview today and what we do in this respect. So maybe some words to myself. Yeah, Sebastian Nold, I'm with Fraunhofer now 16 years and in the research department of photovoltaics, and I'm assessing in research projects PV production technologies, and also within industry projects where, and my colleagues, we are transferring technology to the industry. We'll get a little overview at the beginning of that. And yeah, we're guiding PV development, new PV production facilities along the PV value chain. And I'll give a short introduction to this in a minute, because this is also the basis of our LCA modeling. First, some short introduction to Fraunhofer. So Fraunhofer is a Fraunhofer Institute for Solar Energy Systems, so all around solar energy systems and beyond. And we have a staff around 1,500 people, and in 2023 with a budget of over 140 million euros. Our institute is divided into different business areas. So I'm in the business area of photovoltaics, production technology, and material cells and modules. Also in the photovoltaics field, we have PV power plants, and beyond, we have climate neutral heat and buildings and integrated photovoltaics. They have also an interconnection there. And further downstream, we have electrical energy storage, hydrogen technologies, power electronics, and grids and system integration as business areas in our institutes. Coming to the PV production part in our institute. So we do development from ingot wafer, solar cell, and PV module. We do it on small devices, but also transfer to industry. And for this, we have our PV tech laboratories. So in Halle, Germany, we have our ingot wafer facilities. In Freiburg, we have the solar cells. You see at the left, the front end, so the first part of cell manufacturing, and here in the middle, the back end with the metallization and structuring part, and then the PV module. And we transfer from small devices to large devices to industry, our technologies. Also, we have CalLab for cells and module, where we are testing in our accredited test labs, solar cells and PV modules. And also we have a test mode, so durability tests for PV modules. And what I'm especially working in is technology transfer. So we guiding new entrants and in the PV industry, but also existing ones with technology assessment. In the left part, you see a cost analysis, which we have done for different solar cell technologies. This goes then over when a client has selected a PV technology for setting up PV manufacturing, that we help also with the concept and the basic engineering of this factory. Here's the layouts in the left of a cell and module factory, here in the middle of a ingot wafer factory. And this goes further until ramp up and also training and support of the people, and also until testing of the products coming out of this new facility. So, and this is also then the data which we have gained over the years, coming from research, but also coming from industry, we use for our bottom-up material flow analysis for PV production. So we do from the individual equipment and even bath or chamber in the equipment, material flow analysis, what energy does it require for water footprint, gases, etc. And we do this also in the next stage after first static analysis, also in a dynamic way for, so we build digital twins of PV factory, and all this data is used then for different assessments. One important assessment, also total cost of ownership. Today we'll talk about life cycle assessment. We also look into resource criticality. How does certain technologies have an impact also in the future? How much resources are available? And as said before, we also support in production planning, business plan development, and also what is also important to look at what will be the future levelized cost of electricity of PV of a certain technology and energy payback time. So here is short insight on the bottom-up modeling. What we do here as an example, this graphical representation on the right should represent a solar cell factory with wafers coming in here from the left to the right, and we do the modeling on different levels. So level 1 in the end is here and here you see one machine. So one of these boxes represents one piece of equipment, and here this at the top represents a inline wafer etching machine during the cell manufacturing process. And this consists of different baths. And in research projects with the colleagues of the wet chemical department, we analyze their new developments in terms of cost and LCA. And in industry projects, we use the data from industry equipment manufacturers to analyze their material flows when it comes to existing products, equipment products on the market. Here you see this consists of different baths with different chemistry solutions inside which the wafers go here represented from left to right, and all this data is required to assess how much water do you need a factory, how much of each individual chemical or gas or metallization paste, etc. So for this we do an input and output modeling from the equipment, but of course this water coming in needs to be ultra pure water, but you don't get this from the tap, so it needs to be cleaned, or at the incoming flow or the outside it needs to be treated, gases and chemicals. So we also then at the next level, when we have all the production flow integrated, the supply and infrastructure to this, there will be additional equipment required for this, as well as the building energy modeling on top. You need to have a certain temperature level, and depending on which location you put a PV factory, the energy supply may be different. And you have you can have synergies if you put, for example, wafer and cell manufacturing in the same location. So in some projects we also look into this, how much synergies you can draw from this side. And we also do use different modeling tools for this. For example, then we do, or the colleagues rather, the chemical department do bath simulations of the wet chemical baths, and we have different tools for doing dynamic models on utilization of the factory, also in the end, especially in industry project. And then this one side is, of course, the cost model, the total cost of ownership analysis, for example. The other side is also then the final output of the product. So the efficiency of the solar cell coming out here. This is a publication which we're publishing some years ago on the future of different tandem technologies and what kind of different bottom cells could have an advantage from one to the other. Here we teamed up with the teams with the group of the optical and electrical modeling of this tandem cell. We were defining a process flow, how this could be manufactured, and put this together for these different devices we were comparing. And so this was the cost of ownership, but you have to also go one step beyond. Different PV technologies may have a different energy yield. And so this also then is then the final impact of CO2, or here in this case, cost per kilowatt hour. In the middle, we have cost per watt peak. We'll come to this also in a minute when we come to the LCA analysis. So we're looking through the end of the value chain to compare technologies. Here, I will not go through this, some selected publications from our team. And today I'll talk about the global warming potential of photovoltaics with state-of-the-art silicon solar cells. Here we had a talk at the UPSEC 23 and also published last year in 24 a journal paper on this. And I'll show you some insights from this. So after you've understood now how we do the bottom-up modeling, I'll show you then the different influences which come beyond even the technology selection. So the motivation was that of the analysis on footprint was, of course, we have much more PV coming up and being installed, especially in Europe, which is important for us, but also globally, of course. And it was then the idea to understand better the carbon footprint of a PV system, depending on the manufacturing location, the installation location, and the lifetime of the PV system. And yeah, here, what is then important to note when we come to this, there's the carbon footprint currently used in databases like the EcoInvent database, for example, is outdated. And this was one result also of this research. Here, I give you a short overview in the PV value chain. Here, a really nice graph from NREL on this. So you start with silica mining, and this gets then reduced, the silicon oxide to metallurgical silicon, which is used in various industry. Then in the photovoltaics and the semiconductor industry, we use polysilicon, which is refining this to ultra-pure silicon. This ultra-pure silicon is used then first for an ingot production. Then you have nowadays typically round cylindric shaped ingots, which get then sliced into wafers and then produced solar cells made out of it and then interconnected in a PV module. So this is the classical PV value chain. And of course, important is also then the installation location after it. So what did we do in this study? As just shown, this PV values stage, we have this at the bottom. And we used the ISO standard, which was before also introduced by Ilham, which is standard SEA standard, and the IA PVPS methodology guidelines as a background, and analyze this with the PEFCR category rules from the European Union. And we investigated 3 production locations, which here is one of it is China, where most of the PV models come from, as a high CO2 electricity grid or CO2 emissions in the electricity grid, Germany as a medium representation, and Norway as a low emission representation. Then we were looking at 6 installation locations, which are indicated here in green. So in 6 different climate zones. And we were then comparing what is the influence of the system lifetime, 25, 30, and 40 years. Here you see a representation of the system boundary and what we were mainly influencing from the production side, which is the electricity mix coming from the grid. You may all know that the production of PV, especially silicon, is energy intensive and for a high share using electricity. So in the modeling, throughout the full model which we built, we were adapting or changing the foreground electricity mix, China, Germany, and Norway, and also for the aluminum ingot production, which has a significant impact, one on the frame of the PV module, but also of the balance of the system. And just as background information, we have 63% electricity share as global warming impact in the production of a Chinese glass backsheet module, and 53 of a European glass module in the end. Glass has a lesser electricity share because you have a higher natural gas share in glass production. What was not modified was the electricity mix to produce the background materials, such as the medium ingots and others which we have not a direct control over, which is actually Here it's written correctly. I said we changed it, and yes, we did. So we had a Chinese electricity and a European ingot production bit, because you can find this in both regions. What is important to know, the impact of a electricity production source like lignite, hard coal, or oil or gas have a significant higher CO2 emissions when producing electricity. The data you see on this graph right is coming from the EcoInvent 3.9 database. So we see that from a lignite and hard coal and oil, we are over 1,000 grams CO2 per kilowatt hour for producing electricity from these sources, whereas the renewables are much lower. Photovoltaics is shown here as 90 and in this database, which means then from the average number used lignite in the EcoInvent database, there's a reduction of over 90% when using it within this database. But as said before, the data in this database is old. Same as the electricity mix in the database at the time where we did the study. So at the time where we did the study, there was 3.8 as electricity mix available. There was China data from 2014, there was German data from 2018, and Norway data and electricity mix of the country of 2018. We wanted to update this to the newest year we could find consistent data at the time, which was 2020. We did the study in 22 and 23, and which you see that over time, the electricity mix in China has changed significantly, and it also changed in the other countries. So the share of hard coal, for example, in China was going down from 75.7% to 62% over that time period. So it's important to know from what date the data and from what sources is it coming from. So if you compare this, so what you just have seen, just within this time span, that the CO2 footprint in China has reduced of 14%. The same, the location difference, if you look here from China to Germany, you have less than half of CO2 footprint from Germany 2020 compared to China in 2020. What we also have seen here, that the CO2 footprint from these sources from Norway also changed, but on a very low level. And this was explained, or could be explained, by having more wind in Norway than before, and this having a higher CO2 footprint than hydropower. So now coming to the results. So what you see here now is the bars of the global warming potential, so the CO2 footprint of a PV system. So in the more greenish part, you see then the silicon and wafer production. So the top part is here, the ready wafer. Then we have the cell production in orange, and in yellowish, the PV module production, and also separated, for example, the frame and the glass from the other PV module production. The grayish part on the top is then the balance of system, so which is the inverter, the structure, and cabling of the PV system. So you see this, so the PV module is approximately half of it. And what we also see, that the global warming potential here differs significantly on the manufacturing location. And as shown before, also which electricity mixes we use. We have here, for example, a 7% global warming potential decrease just using newer electricity mix data. Then also we have more than 43% global warming potential decrease coming from China to producing in Germany, or 58% global warming decrease when all the modules were produced throughout the full value chain in Norway. So what you see here in blue is the global warming potential per watt peak, so per nominal power of the PV system. On the left, you see in grams per kilowatt hour produced over the PV system. Here we use the PEV-CR category rules, which were then, and you see it here described on the bottom, so with 30 years of system lifetime, and we were analyzing this at a location in Central Europe, or rather southern part, I would say, of the Europe. And we, with our newer data, so we were using our own technology data. It's also linked in the paper, but for a PERC technology, which is actually also transitioning out nowadays. But we come, and even when produced in China, to a global warming potential of only 40 gram CO2 per kilowatt hour. You've seen at the beginning that in the Ihoume database, there is more than double listed as a PV technology. And we know that the data the Ihoume database used for PV is for a very outdated technology, which is more than 15 years old. But if you look then also at the other variables which we've analyzed, so on the right, you see in a graph for different manufacturing locations. So the top graph, you see all bars are representing manufactured PV module in China. In the middle is manufactured in Germany, and the bottom is manufactured in Norway. So with the same module, we can calculate, depending on the lifetime and in the installation locations, a very large difference. So same technology, other manufacturing location, other installation, is a factor 8 difference. So we calculate the high irradiance with a low CO2 footprint module below 10 gram CO2 per kilowatt hour, but with a lower irradiation and manufacturing in China over 50, still lower than the data the Ihoume databases presents. If you compare at the same technology, but with a different production electricity mix, but installed at the same location with the same lifetime, the global warming potential differs by a factor of over 2.4 we calculated in that example. And the influence of the installation locations, we have approximately a similar spread. So here in the middle, for example, German-produced module, but installed at a temperature coastal climate with 25 years lifetime, also 25 years lifetime in a subtropical arid location. If you see here the climatic data sets and the radiation we have used on the left, then we see a spread of 2.3. And if we just compare at the same location a longer lifetime of the middle of the PV module or the PV system, then we have a factor even 1.5 in different in the global warming potential. So you see that the global warming potential of a PV system can differ a lot depending on these three factors. So the production location, the installation location, and the system lifetime. I'll come to my final slide to wrap it up. So as said, the production location lifetime and can have a high influence of the global warming potential with a factor of 8. And current calculations, and I would say they're even newer coming up. We're just working on the updates from the IEA PVPS Task 12 from the current TOPCon technology, which is now dominated in the market and will even show lower results as what we've seen today. But what I showed you here in this analysis, we show significant lower global warming potential, what you find in the databases, less than half. And the most classical, I would say, case is produced in China, installed in the EU, at least from our perspective. And we used here 30 years lifetime is, for example, at 36 gram. So at locations where the good solar radiation, this PERC system can even have a lower global warming potential than wind energy. And even beyond the global warming potential can be lowered or is lower, I would say, with current technology. And if you source your background materials also from a location with a low electricity mix or with a low CO2 footprint of manufacturing these materials. Thank you very much.
Thank you, Sebastian. Really on time. Very good. as I said, we will conduct the questions after. I have some questions, so actually, but I will wait for Michiel when he. So I think now we will do just a small break for coffee. Since we are a Swedish institution, we need to drink coffee every 2 hours, or every 1 hour. So after the coffee break, so we'll be back at 2:20. Michiel will take over, and we go from there. So I will ask people to mute and shut off the cameras and can go for a coffee, and we come back in 8 minutes. Right? Okay. See you guys.
This webinar, the recording is in progress, so that's great. And I will take over hosting the second part. My name is Michiel van Noord from RISE Research Institutes of Sweden. And our next speaker is Dr. Burçak Ebin. He's assistant professor and senior researcher at Chalmers University of Technology in Gothenburg. And Burçak is also the director of the Swedish Competence Center for Recycling. His expertise is mainly in recycling of PV materials, of battery waste, and also industrial waste. And as André mentioned earlier, Burçak is also an expert in Task 12, IEA PVPS Task 12. And apart from that, he's very active. He's also a co-founder of a startup company looking into the recycling of transparent conductive oxide materials. And that, I think, is also linked to your speech, Burçak. So you're going to introduce us to the critical role of silver and indium recycling for PV sustainability. So please, the floor is yours.
Thank you very much for this nice introduction. So, yes, and then I don't need to focus on much. So then I will deep dive a bit about the silver and indium recycling for the PV sustainability, because I believe that it's one of the important issues we will handle in the next few years. But before that, you also mentioned that I am the director of the CCR. Maybe it can be kind of confusing, or our audience might want to know a bit more about the CCR. CCR, actually, we are an active platform to improve the collaboration between the academia, research institutions, and the industry. So the main goal is actually to join the forces to recycling or waste management much more economical and then much more feasible. So for this purpose, we have a kind of the different activities to improve our collaborations. So actually, as a competence center recycling CCR, we are doing different activities covering from the basic webinars or project applications together with the partners as well. So today's topic, I am sure that most of you know about how we are improving our PV installation. And then we have a very ambitious goal as the International Energy Agency. So then the goal is almost reach to 20 to 25% of the global electricity generation in 2050. That ambitious goal actually also will have drawbacks for us, because actually we will create some kind of the waste. So when we think about this, the ambitious goal, we will actually start to create some waste. When we check for the different analyses from the IRENA or International Energy Agency report, in 2050 we are expecting between the 60 to 78 million waste. But then that was a report was 2016, and then a recent research also shows that it will be a bit more than they expected, because actually we start to implement much more than the targets. So, but when we compare this, the PV module waste volume compared with the other waste, like in the municipal waste or plastic waste, actually it's really small amount. But why it is important to recycling of the current PV models? That is the key point. Because in all of the PV models, we use critical raw materials or critical and strategic raw materials together with the silicon. And then these ones is also the small amount in the PV models. When we think about it as a PV module, the main amount is the glass, aluminum, and plastics. But almost the 5% actually includes the strategic and critical raw materials for us that we have to handle. So I'm sure that most of you know about the different kind of the PV module types, because we don't have only one technology. There is different technologies, including the silicon-based technologies, thin film technologies. We have the organic, perovskite, or the more futuristic tandem or multi-junction photovoltaic technologies. But all of them have one common point, which is actually the silver implementation as a conductive line. Almost all of them, we need to use the silver for the conductive lines. Besides, for the new technologies, like in the thin film solar cells, such as for the jigs, or for the perovskite, for the organic, for the tandem, or for the heterojunction solar cells, we need also the transparent conductive oxide layer, which is mainly used ITO, indium tin oxide. So in here, there is two common points. Silver and indium tin oxide is almost, except the old silicon technologies, need in the all different photovoltaic technology. So when we focus on this, actually, material supplies for silver and indium, it's not something actually studied for today. It have a long-term investigation. And then in 2011, it was for the first time stated that silver and indium availability will be the bottleneck for the silicon and jigs. And then in continuous research in 2015 shows it more in the graphs about what is the watt production for indium and silver, and then what will be the need for the solar industry. And in 2023, another report also showed the same points about the indium deficiency, that to reach the intended targets to implement the photovoltaics. So then in all of them, actually, from 2011, it's a clear sign that we have a problem about the silver and indium. And in a recent research from the last year, it shows the same problem. Silver and indium will be the problematic for the next 5 years. So those are the actually will be limitation for the photovoltaic technology as the raw material. But why not we don't produce more? Because it's not that easy. These materials, especially the indium, it doesn't have their own mining. It's a byproduct. And the silver is also produced as a byproduct, but it has also own mines. But producing a byproduct is not easy as it is in the main product, because actually we need to produce something else to produce the indium. And it creates another challenge for us, so we cannot actually mine more. That's the reason we have to focus on their recycling. Of course, there is a good side that by time, there is a simple explanation for the silver. We reduce their consumption in the solar cells because of the increasing the PV manufacturing technologies. We can reduce their implementation also, but it's not change everything, because we will need still to recycle these materials. That's what we are focusing in here in our research at Chalmers. So we are focusing on the jigs model recycling. Of course, the important part of the delamination of the cells, And then we focus on the different approaches. One of them is the leaching with the different acids. But when we come to the standard leaching, we realize that because of its layered structure, we can actually selectively remove some layers. And then with the implementation of the ultrasound power, it is actually the step-by-step remove the specific layers, which is ITO and silver. So we focus on our research in this part, and then step by step analyzing the ultrasound power, we can clearly see that by removing the down layers, we can remove in the first step, we can remove the ITO, and in the next step, we can remove the silver. But as you can see, when we are working in this in between, we realize that there is still some kind of the ITO left over around the silver lines. So then we focus on a bit optimization of that processes. So when we focus on the optimization part, in the first step, we actually leach to the down layer, which is actually the main zinc-rich layer. And then we only have a really small amount of the indium loss in the initial leaching. Then we can recover the ITO layer as it is, as the ITO-rich particles with a minimum amount of the impurities. And then ITO recovery reach 99%, and then purity is directly 70 in one-step recycling method. That is actually give us a really good base ground to increase its purity. In the second step, we continue with the same material, and then actually we succeed to remove the silver by ultrasonic treatment. And then in this step also, we only have the really small amount of the impurity of the indium and then some others. So then almost the purity is almost 99% silver. So we just consider about that. Why not we can go on the same approach to the silicon PV modules. So of course, at the same time, we have to terminate. There is a kind of the different termination processes we have been working in Chalmers, like including the combustion pyrolyzers, hot knife, and supercritical fluid. And then to understand it, first we start with the leaching and some purification methods. But after a while, we understood that with the etching of the surface, which is the silicon nitride layer for the silicon PV modules, we can actually remove the first touching layer. By removing this touching layer or disrupting this layer, we can understand that with the ultrasonic treatment, we can release the silver contact. By releasing the silver contact, we can, with a simple method, we can actually purify the silicon wafer, and then removing the silver contact, we can obtain the high purity silver. So, since due to the time limitation, I will summarize my general work in here. As I mentioned that silver and indium supplies are the bottleneck for the sustainable PV industry. And combination of the selective leaching, or we can say the etching, and ultrasonication is a promising approach to recycle the solar cells layer by layer, specifically silver from the silicon and then silver and ITO from the GIGS solar cells. But in here, we have to consider that the process was from the cells. So then the elimination of the modules is an important and a key factors for efficient recycling of these critical elements. And when we consider the current study of the waste management, PV recycling processes are not economically attractive due to the limited of waste. Of course, it will be more. but it is also challenging in the recycling of the critical and strategic metals because of their low concentration in this waste. That's the reason a unified recycling process is suggested in here, etching supported by the ultrasonication. It can be attractive to improve the PV model waste management because we can treat the both silicon and other different kind of the thin film solar cells. Before finalizing this research, I would like to thank our team. Of course, not all of them is working right now. All these years, all the people supported all activities. I would like to thank all of them. And you can find our research in this or previous papers, and our PhD student Iona Teknets also recently graduated. So you can find all this research in the Chalmers webpage. One last point I would like to mention, we are organizing a conference, Circular Material Conference in 2025. We have different focusing, but one of our key point in this conference is sustainability of the photovoltaics and solar panels. So I would like to invite all of you if you have time. So thank you very much for your attention.
Thank you, Burçak, for an interesting presentation and good to remind us of the conference coming up. And that was our first speech on the on recycling, and we move on to a second speaker regarding PV recycling. It's Dr. Rune Søndenå, who is a research scientist at IFE in Norway, the Institute for Energy Technology. Rune has a PhD in chemistry from the University of Oslo, and his research is focusing on recycling and sustainable production methods for PV. And he is involved in the Retrieve project and will tell us more about the recycling of end-of-life silicon as they work on in this project. So please, Rune, go ahead.
Thank you. Am I sharing correctly now?
Yes, that's correctly, and we can hear you clear.
Yeah, perfect. So thank you for having me. I am presenting Horizon Europe project we have running. We are coordinating from IFE. It's called Retrieve, and I will talk briefly about our efforts to recycle end-of-life silicon. We touched into the problem briefly in that last presentation. If we fulfill our plans within Repower EU and build out the PV according to the plan, we will end up with a mountain of wastes generated. And I think our own calculations, by the year 2050, we end up with 700 Eiffel Towers per year of waste generated in the world. And one Eiffel Tower is 10,000 tons. So it's a nice round number. So perfect units for waste, I guess. And it's a challenge. And if we don't do anything, it's going to be a lot of material that we need to put in our landfills. And the second half of the problem, silicon, is on the critical raw materials list. And it may seem weird because in Norway we do have mountains of rock available. But basically silicon is on the critical raw materials list because almost all of it is produced in China now. So we're depending on one country and one country only for our silicon production. Well, these numbers are from 2021, and things have not improved the last couple of years. I don't know what will happen when the IRA kicks in, if anything will be moved to the United States, but for Europe, it's not looking promising. So it's the second part of the problem, and we all know that solar panels, they're not waste. A lot of energy has been put into purifying the material. It's really pure material needed and used. So the glass, for instance, is low in iron, low in sodium. It's a very pure glass, and silicon as well. It's up to 9N purity for a solar grade silicon. I guess the bad news is, according to this Waste Electrical and Electronical Equipment Directive, only 80% of the solar modules have to be recycled. Basically, if you recycle the glass and recycle the aluminum frame, then you have covered what you need to recycle. You have covered the 80% of the weight, and you don't have to do anything else. I believe recovering the silicon is already profitable, but technically you don't have to do anything else. The good news is that most people in Europe have higher ambitions than just recovering the glass and the aluminum frame. So there's quite a lot of activity going on recycling of modules, and there certainly is value in the material, I hope. The trick is to find the direct value chain to use. And Retrieve, it's a Horizon Europe project, 18 partners in 10 different countries. We have a budget of 9 million euros, roughly, 7 million from the European Council. And we are covering a lot of the value chain, a lot of the PV value chain. We have some operators of PV plants. They're also the people making the decision on when to decommission plants. We have some dismantlers and recyclers on board. I think the weak link is the solar cell production. We don't have any industry partners doing solar cell production within the project. It was difficult to find that in Europe. So the silicon or the solar cell production is covered by the industry, by the research partners in this project. And we also have some non-technical tasks with digital product passport development and some LCA involved as well. The main idea of Retrieve is to go for closed loop recycling. We're going to try to bring the material from a solar cell back into PV. And mainly the glass and the silicon will be put back into PV. I think in the case of metal recovery, especially silver, there are functioning markets. So in those cases, we're going to be happy if we can make a product that we can sell. And we're also trying to make something useful out of the polymers and not just burn it, calling it thermal recycling and burning it. We're trying to do something slightly more advanced than that. And the focus for the rest of this presentation will be on the end-of-life silicon recycling. We are trying to get that back into PV. And the standard process for making silicon starts with making metallurgical grade silicon through a carbothermic reduction of quartz, and basically mixing quartz and carbon together and heating it up. Goes without saying that we are generating CO2 and carbon monoxide as well. So it's the carbon footprint is high in this process. And the purity of the metallurgical grade is about 99%. And since this is normally the starting point for making solar grade silicon, this is the material we are hoping to replace by recovering and recycling the end-of-life silicon from discarded modules. And the question is, where do we need to input this recovered end-of-life silicon into the value chain? And it is tempting to input the silicon as late as possible in this process. Just direct remelt in the silicon or in the ingot production. It would be ideal. Then we're saving on the purification and basically using or cutting the CO2 footprint as much as possible. And question is, can we do this? And it has been tried. In China, Trina Solar has tried this direct remelting of end-of-life silicon. I think they are lucky in China. They have potentially some production waste as well they can recycle. I suspect that they have also mixed in production waste so that into this recycling, because anyway, they are managing to make solar modules with a 20.7% efficiency with this direct remelting of recycled silicon. And comparing to their standard module with virgin polysilicon, that is 22.5% efficiency. So there's a penalty of roughly 2% absolute. And I'm not sure, but I suspect that if you're trying to sell a module that's 2% absolute lower in efficiency than a conventional module, you're going to struggle. I don't think you can give them away again anyway. So I'm thinking 15, 20 years of energy production from a module operating at 2% lower efficiency than it could have been. I think that's a bad business idea, and I don't think this is a viable approach at all. And at the same time, this is a fantastic graph from Q-cells. Shows the gradual improvements, every single improvement Q-cells have had in the last 15 years, starting at 17% in 2010, getting close to 26% in 2024. So every point here is one improvement. Some of it is material quality, process improvements, so some additional processing involved. And this also shows in addition to the gradual improvement, it shows the more abrupt changes in technology. So changes from aluminum back surface field cells to the PERC cell, and they change to the TOPCon cell. And this, it's a fantastic development over the last 15 years, but it also shows the challenge. We are typically trying to recycle modules that are 15 years old now, and it's a completely different solar cell that's being produced now. So we're not recycling, we are in reality upcycling the material quite a bit. That is half the challenge, and the second half is the rapid technology shifts. And we have seen the last few years some really rapid changes in the market. Multicrystalline wafers disappeared in a couple of months in 2019, I think. Gallium replaced boron as the p-type dopant of choice virtually overnight. Right now, we are seeing a change from n-type technology, from p-type technology to n-type technology. And when these changes kicks in, it always happens faster than expected. And even now in n-type technology, we're seeing some tests with alternative dopings with, for instance, antimony. So it means that, again, the material we are recycling, 15-year-old material, it's not the same as they're using in silicon and in solar cell production right now. And we in Retrieve, we are working on a couple of assumptions. End-of-life silicon will be boron doped for quite some time yet. What we're typically seeing now is 15-year-old modules being sent for recycling. And based on all of this, we think that purification is needed. Yeah, well, most likely. Yeah, the shift to n-type is strongly connected to the shift to TOPCon. So basically, with this recent shift to TOPCon, the n-type is coming. So we expect n-type to completely dominate. Well, this year, 2025, n-type will dominate, we think. So message purification is needed. And the way we see it, boron is the problem. In the regular P-type silicon containing boron, we see a degradation of the lifetime when the wafer and the cell is first illuminated. We have light-induced degradation. The lifetime can be reduced by 90% of the initial minority current lifetime in the wafer. And that is something you will notice on cell and module performance as well. And unfortunately, if you have N-type silicon with traces of boron, you will see the same degradation. It's not as large, but this degradation it's quite detrimental if you're trying to make an N-type solar cell out of materials containing even a little bit of boron. So that is the challenge, removing boron. That's the way we see it. And that means that we do need additional purification. We need to do something to remove mainly boron. And we do have some options. We can go for metallurgical purification, vacuum, or steam purification, or the conventional chemical purification. That will be the Siemens process. And we start with the metallurgical purification. We used to have Elkem Solar Silicon in Norway. They unfortunately closed down their production about a year ago. And I say unfortunately because they had a fantastic technology where they used 100% silicon sawdust as a starting point. So they had the option of making solar grade silicon with an extremely low CO2 footprint. But they were struggling with exactly that issue of removing boron. And I don't know if that played a part in them closing down, but it was a problem. And a second approach, vacuum purification. As far as I know, this has only been demonstrated in a lab scale setting. I think a batch size of 400 grams has been tested. And again, it is a challenge to remove boron. With the plain vacuum purification, only phosphorus is reduced in this silicon. And if we want to remove boron, we need hydrogen or steam actually to extract the boron, and it's a challenge. And we know that we need to get the boron concentration way below 1 ppm, and I suspect it will be challenging. It's an interesting technology. Just like metallurgical purification, we deal with molten silicon in a liquid phase, so we don't have to convert it to a gas. So it's a potentially energy-saving technology, but the removal of boron is a problem. And that leaves the conventional way, chemical purification. Well, this is the process we usually call Siemens process. It's a bit more involved. It starts with the hydrochlorination, just converting metallurgical grade silicon, or in our case, end-of-life silicon, to trichlorosilane using hydrochloric gas. Typically in a fluidized bed reactor, starting with tiny particles. So it could be ideal for starting with crushed silicon from a module. And there are several different options to choose from here. So it could be a separate presentation to go through all the options here. After hydrochlorination, there is distillation through distillation columns. So light complexes will float to the top of these columns and will be extracted. Heavy complexes will float to the bottom. Just basically normal distillation of a gas. And the last step is what the well-known step, the Siemens process. And basically when we are lazy, we just call. We usually say the Siemens process, and we think of the whole process. So just calling it Siemens, the Siemens process, is a bit misleading. But this is the one we know about. Basically, that is the option we have chosen. We believe in the Siemens process, and what we are working on now is finding practical solutions on how to solve this. How do we get our end-of-life silicon in a format that's suitable for the Siemens process? There are a lot of different technologies to choose from on the dismantling side. One normal way of doing it is crushing and milling the solar panels and then sorting afterwards. We have seen that usually leaves quite a lot of glass in with our silicon. It could be quite a challenge to separate that afterwards. A hot blade technology where we separate the glass first seems really promising. That will the result is it's much purer silicon afterwards. One problem there is that we have seen that a lot of the modules, when they are discarded, they are broken. The people doing the dismantling, they don't really understand that there is value in unbroken modules. But absolutely a promising technology. There are other ways of solving this, layer by layer removal with water jets or even sandpaper. Laser separation has been proposed, and you could even do it with cryogenic separation. But it's challenging, and part of the problem is that solar modules are made to last 25 years, so they are put together really well. We didn't really plan for recycling when we made them, at least not 15 years ago. So I think that brings me to the summary. Recycling of end-of-life silicon, it is a challenge. It must be considered upcycling, but there is a lot of value in the material. So hopefully we will find some solutions for this. And the way I see it, the way we see it, is that boron is the main challenge. Basically because of all the gradual improvements and also the technical changes. There's a lot of work being put into finding technical solutions to separating the material. On the last slide, I showed there was a lot of different approaches proposed, and it's promising. I really think we will manage to find good solutions for separating the material. And what remains now is to find the correct way to recycle this material. Whether or not if it's back to PV or if it's other value chains, that is the correct way. But our approach, we are testing closed loop recycling through the Siemens process. And if you want to know more about our project, you can visit us in social media. Thank you for your attention.
Thank you, Rune, for a very interesting presentation. And also thank you for being in time. I think our presenters have been really great today. Everyone has kept their time, which means that we have about half an hour time for questions, discussion, if you like. We're gonna I hereby also invite you in the audience to put your questions either by raising your hand or writing a question in raising your hand, and then I can yeah, how to say, manage who is speaking. Alternatively, if you want to write your question in the chat, and then we can put it there.
Michiel, I can check the chat for you. So
Great. That's great. And I can start by I think one question. Of course, now we're I think we will mix somehow questions regarding LCA and recycling. I think we can do that, and it can also be useful. And one aspect that I think some of you touched upon, both regarding recycling but also regarding LCA, is related to European production or production in Europe or regionally. I was thinking from that perspective, if we look at recycling first, I don't know, maybe a question to you, primarily, Rune, do you see that having a local production of wafers, ingots, cells, would that be a prerequisite for doing this end-of-life silicon recycling, or how important for the recycling process, for a high-end recycling, is it that we have PV production in its different steps locally? Do you have any thoughts on that?
That's a very difficult question. It would be helpful to have solar cell production in Europe, and to partly to keep the competence on how to produce cells in Europe, and also to have a market for the potential production of silicon or solar grade silicon from recycling. Because I would totally expect that it will be challenging to not handle our own wastes. I would expect recycling will have to be done decentralized, based on problems with logistics, and also with the ethical aspect of not exporting our garbage to other parts of the world. As a rich part of the world, it's challenging to send our garbage to other parts of the world and assume that they handle it responsibly. So from that side, it seems reasonable that we need recycling in Europe, and it would be nice to have the market and the off-takers of the material also in Europe.
Yeah, and if we don't, then maybe a follow-up question. If we do not have that, what you mentioned, I think also other industries, maybe it's also an option to export our silicon waste to where we do have producers. But what other industries do you see could be interested in using silicon waste from end-of-life PV?
Well, we need an industry that is big enough to handle the large masses of silicon that is recovered, and one obvious industry would be the battery industry. So if we are able to use silicon as an anode material in batteries, that is one potential off-taker of the material, and to some degree that would solve the problem with the dopants, because I think the requirements are lower with respect to the dopants in battery use, and it also allows us to call it high-value recycling, I guess. I think adding it in metallurgy, using it as an additive in steel production, for instance, is also an option. It kind of feels like we're not using the full potential of the recycled material, but it's potentially there, and I expect the LCA calculations might help us decide what's the most sustainable option.
Yeah. Thank you. I think Burçak, you're working also with recycling of batteries. You're already raising your hand. Yes, I thought you might want to comment on on this, on battery industry or
Yes,
maybe other industries.
yes, exactly. So then, first of all, when we think that right now almost 95% of the market belongs to the silicon-based, and then the forecast shows it will not change that much. So then we will still, the market will be dominated by the silicon-based solar technologies. Of course, there will be niche technologies, but it will be a bit less than the silicon. So then, in that sense, as the Rune mentioned, that the silicon recycling become critical. But the important part for the recycling is the value chain as well. So when we considering the recycling, we cannot actually ignore the production or manufacturing of the PVs. Because right now we are talking about the recycling in Europe, but it's always mentioned that we need somebody to use it. Otherwise, there will be no need that much recycling. So that's the reason it's important to develop the initiatives in Europe to process the silicon, high purity silicon. And then Rune also mentioned that they couldn't find a partner, industrial partner to do it. So we have the research institutions, but unfortunately we are lack of this competence. So because when we are thinking about the volume of the recycling materials, so then right now the China and also the India is growing in the silicon manufacturing, also same as the Japan. So then they will not consider to get all West to process this one. They are already doing this, or they will already do that. So that's the reason it is so important to create a value chain within in Europe to reduce the transportation related cost and the transportation related CO2 footprint of the whole line. And then considering the using the silicon in other applications, it's important. It needs to be the analyzed. But right now, the lithium-ion battery industry, they have already settled on specific anode type. They can slowly change it, but it will not dominate the whole market with the silicon anode. At least that is in the short-term perspective. And then there will be some approach to use the silicon, but it can be mainly for the coating on the anode surface and similar applications. But still, the vast amount of the silicon cannot cover the enough or for the battery technology. So then we have to create or consider a total value chain to continue for the recycling of the silicon as well, and also considering the other raw materials, of course.
Mm-hmm. I see. So,
Michael, you have
yes.
Michiel, you have some questions online. I don't know if you want to go first around the group, or you want to address the ones that are online.
Yes, I mean, I think we have one question, a specific question I saw also to Burçak.
I think it's good for merging these two worlds. There is one that I will summarize that basically, should we make modules easyable, recyclable or not? So it's about that thematic that I think it's connected a bit with LCA too. That because as Rune said, there is a reason why they are difficult to recycle. It's because they were designed to last longer. And then when you calculate LCA, we also take in account the lifespan of the module. So there is this fundamental question. I think it will be hard to have both worlds. So I would like to have maybe the comment of everyone in the panel, this recyclability versus lifespan. What is your point of view on this? I don't know who should start. Michiel, you can be the maestro here.
Yes. Maybe if we move on, maybe we let Sebastian start, and then we go on. I think
Maybe yeah. Also from looking from the manufacturing side, but it was
exactly.
also said before. You have to sell this product in the end, and the market is of course then looking often at high efficiencies. And if your module with a recycled silicon in it, for example, has 2% less module efficiency, first it will be maybe overlooked because people are looking on the highest efficiencies. Secondly, if you use that silicon again, it may not be sure that you have a lower CO2 footprint, for example, in the end, because efficiency has an effect on the overall energy yield, right? So, and if you use then the same materials for everything else, for them it will be worse, but just for this one recycled material, it will be better. So you have to all overlook over the whole cycle in the end. And research, of course, often looks then of making the existing process better. And recycling, there of course have been recycling projects in the past, like Rune one shows. I know from the colleagues also in the past that they have been trying years before also to use recycled silicon in multi-crystallization, where our colleagues years before have done a lot of work in, and this efficiency gap was hard to close, or it's always been there. So my personal take is maybe put the silicon you use recycled in the polysilicon step. So in the entry of the polysilicon manufacturing and all the cleaning and then recycling, then it's already can be a closed loop system. So that could be also an option to use this recycled silicon. But I'm not an expert on silicon purification in the end. But this I think is then easier, and you will get the same product in the end as a polysilicon out. So you have to look at the whole cycle and all the materials, and efficiency matters. Let's put it like this: energy yield matters on all of this, on costs and on LCA.
Yeah. Yeah, and I mean, you showed the impact of different climates in relation also to different lifetimes. And so, do you want to say something on a more general than only silicon recycling, but the how do you say the balance between making modules more easy to recycle for all kinds of materials and ideas mentioned here in putting contacts directly on glass, for example, and that sort of the trade-off between that making it more easy for recycling and maybe a shorter lifetime or so. What if we look from a carbon perspective or environmental perspective, do you see that there is it an opportunity or rather a risk to make modules that are more easily to disassemble? What do you think?
Reduce the risks during the development in the end. But one thing is, and we had this also before, for example, with metallization. I mean, the industry is working hard on substitution of silver, for example, with copper or also with aluminium. These are options for making lower CO2 footprint contacts. On silicon, printing directly in glass will unfortunately not work because you have to encapsulate the cells within encapsulation for protective reasons, also for not getting moisture on it. So you need to have a direct contact to the silicon solar cell or a tunnel contact, either in the tunnel TOPCon solar cells. But for thin film cells, this is done that way. So you build the cell inversely from top layer on the glass until you have the back contact. But my take would be recycling technology should be able to deal with different kinds of technology. So in the end, the recycling technology should adapt in a way. And I don't think it is such huge of a challenge. There are different ways out there, different approaches out there in recycling. And yeah, so of course, from the recycling side, there could be some requests to do things differently in the end, or some learnings. But in the end, I think has been a lot of research, but when the volume comes, there will be a lot of research or a lot of more practical experience there. And I think the recycling technology will also develop further and adapt. So I would say from this side, there is also a lot of potential still.
Thank you. Shall we continue on our round? Maybe Ilham, do you want to comment a bit on recyclability and environmental aspects and trade-offs?
Actually, it's so hard to answer because there's a lot of factors. And if we think about recyclability and reliability, do we need like models that stay longer and at the same time to be easy to recycle? There's a lot of also parameters. And if we see like the economic side, is it worth it to do recycling? Is the cost, the energy that we need to use? Also, we need some competence. So actually, I don't have a clear answer because it depends on a lot of factors.
Thank you. Burçak, you raised your hand. Want to
Yes,
comment on
thank
this
you.
question?
Yeah,
No.
thank you again. I just want to tell something quick because we're just talking about an interesting topic, and then how we can actually manage all of them, like the recycling and manufacturing. Actually, in here, RCA is really important because we mentioned in different topics that Rune mentioned that silicon is recyclable, but we have to give up from some efficiency. It might be the similar for the different kind of the materials. So then actually there is a synergy between the recycling and then manufacturing of the solar cells again from the recycled materials. And it's the same as day by day actually we reduce the amount of the consumed material in the solar cells or the solar modules, which makes the recycling much more challenging because we have to deal with the low amount of the material, which is not really feasible and are more challenging. So, but where is the point in here that we can combine? It's the RCA. It will let us to understand, okay, we can recycle it, the silicon is a really good example by Rune, but we reduce the final efficiency if we reproduce it. But what will be the environmental impact of the reuse it and then give the another additional life for 30 more years? So that is something we have to consider. It's the same for the all materials that the coating for another material or reducing the amount of the material in the solar cells. Actually, when we consider the also circularity of the metals, how we actually reduce the environmental impact or increase the environment because in the all processes we need to consume chemicals as well. So then that's the reason the heart is in here RCA to understand how the future of the manufacturing and recycling should be shaped. Thank you.
Thank you. Yes, so cooperation is needed between the different fields. I'm also going to ask you, Rune, to comment on this. Yes, this balance or challenge, and I will add also there's another question in the chat also, which is a bit related to this on the use of a tandem perovskite on top of silicon, and would that make recycling of the silicon more difficult? Is it then worth to go that direction? I think it's related to this, making a product that has higher efficiency, but will it make recycling more difficult? Do you want to?
And
Yeah,
also
yeah.
the lifespan, according what they say, shorter.
Yes, maybe also the shorter lifespan, exactly, adding to the LCA perspective.
Yeah, so I don't know what order to. Well,
As you
in
like.
practice, we see that solar cells are made to last 25 to 30 years, but in the field, they are typically discarded and changed a lot faster. So it's 10, 15 years old modules are the ones we are seeing being recycled now, meaning that we might not need them to last 25 years, or there are or maybe it's difficult to make them last 25 years, even though that was we intended. So it's a balance. You want to make the solar modules solid. You want to protect them, avoid water ingress and delamination and all these things, and you still want to take them apart and recycle them. But even if we include some designs for recyclability now, we have 15 years of old modules. So we really just have to adapt to the modules we are getting. And assuming tandem cells, maybe if we assume that it's perovskite based top cell and it contains lead, for instance, and you really don't want that into nature, then you have a conflict right there. But I think it will be worth it. I think we're reaching the limit of our single junction solar cell about now, and it's time for a new solar cell design. And I really think tandem cells are here to stay. And from Burçak's presentation, I don't think there was too much of a challenge removing indium and silver. So a chemical recovery of the top cell, if it's perovskite or other. I don't think that will introduce too many problems on the practical side. So I think the benefits far outweighs the drawbacks with tandem cells.
Okay, thank you. I see a hand from Isanola Soho. Do you want to ask a question?
Yes, I have one question and comment. Like, is this necessary to use this record material from PV cells in same in this PV system, or we can also substitute this material with we can in other production system, because industrial symbiosis approach. So we can use this material, PV recycled material, to another product manufacturing maybe. So we don't need worried, because there are a lot of opportunities or maybe demand of that material can be used to form other products, not put in the same loop. So where we can also use this waste and and we don't need about this life span of this PV cells. So one was this for commit. So it is how this will be impact on our life cycle of this material, and and other thing is, and we also this approach of industrial symbiosis in this whole this system of manufacturing PV cells.
Was that meant for me?
Yes.
I agree.
Yeah, I think Rune, you are the one.
Yeah.
You answer
Yes.
that.
We are testing the closed loop recycling route, and it's elegant. Then you have you're solving two problems, right? You have a market that can absorb the amounts of silicon you're producing, and you're reducing the amount of waste you have to find other use for. So we're testing the closed loop method, but I'm not entirely convinced that's the best option. As it turns out, we need to purify and we need to invest more energy into the material for the closed loop recycling, and it's not obvious that this is the best way to do it, seen from a sustainability point of view. And there are other routes, battery use, metallurgical use. If we go down to construction use, just using as filler in concrete, I don't know what is the best solution, but there are certainly options to choose from.
Yeah, thank you.
Thank you indeed. I see we have also a question in the chat regarding to BIPV. Maybe Ilham, you can comment on that, and then maybe also Sebastian, you can add to that later. The question is if you have studied the cost of service when it comes to BIPV, as maintaining, repairing, etc., would sound to be harder since the components will be embedded in the building.
Actually, in the BIPV side, the module should last at least 30 years. It should be like the same age of the building, because it will be hard to like do maintenance. And also we need to take account the inverters, like the lifetime of the inverters is just 15 years. So when we do LCA, we need to account, like we need two inverters. So yeah.
Okay. And Sebastian, I know that you are also involved in a project looking into BIPV. Do you have any?
Yes, well,
questions
we
for
have been looking more into manufacturing of BIPV modules and not so much into the cost of service. But I would say, following to what Ilham said, that longevity in a building, building integrated photovoltaic is higher of importance. I mean, and that's also then the beauty of PV. Install and forget works most of the time over many, many years on residential buildings. The inverter most of the time is has not that long life and maybe exchanged typical lifetimes 10 to 15 years, but they're more easily accessible than the PV modules. But it's also not rocket science in changing a PV module on the roof, or maybe in the future on the facade. I mean, you would need some scaffolding, but in the end, PV modules, some last very long. Some manufacturers are giving warranties to 25 years. There are even manufacturers out there giving warranties over 40 years. So it's a choice in that perspective, of course, on the manufacturing excellence, but even more on the materials used in the manufacturing process, how long the modules will be lasting, that they do not delaminate, and that moisture comes in, which is then a risk for the PV modules to fail at some point of time. But typically they last very long. So I don't expect this too big of an issue, or at least if we do it right, it may be not. If it's just being about cheap modules, of course, there's a higher risk, and this can be seen in the fields. As also Rune said, repowering or PVs coming to waste today are not that old, and this can be seen in the market, coming also from different reasons. Sometimes it's just more economical, use that area and install PV modules, which now have increased from 15 years ago, maybe 12% efficiency to now 20% and above. Yeah. So that can be much more economical to use that area and just get 50 to 100% more power out of it. So economical reasons behind these also have an impact on recycling, on not essentially that the PV module is old or not usable anymore.
Michiel, can I do a follow-up question about this?
Sure, go ahead, André.
So because of repowering, so there is a discussion about, so if we are repowering in 10, 15 years, the modules supposedly are under warranty. And the question, different projects are working on understanding if we should reuse those modules, where repowering is done because of mostly of the times because of a financial option, because modules are very affordable these days. Should we recycle them or give them a second chance in a context that maybe it's not so important to have so much optimization of energy? So the business model here do you think will affect this, or do you think they will makes more sense to send directly to recycling instead of trying to reuse them if they are still producing 17, 8%, 18%? Do you have any intake on that?
Yeah, maybe a short answer on this. Modules degrade over time, but still over 15, 20 years, they still have 80%, approximately plus minus 10% maybe of their initial energy. So of course they can produce more energy, but it has some economical constraints then in the end of reusing them. And that's what we hear from the industry, of course, is also safety of using modules again. If you have been decommissioned from a previous power plant and sent to another one, there are risks of transports. They need to be checked first also, these modules, if they're all safe to be reused again. There's insurance reasons behind it. If you can insure the new PV power plant with reused modules. So there are many questions behind it. I'm not an expert in that field, but from discussions, I know or know at least these points I can mention here. So yeah, because also safety reasons behind it. So if you have the back sheets of the PIM model having cracks, for example, and you can have, it's all about arcs in the end, or fire prevention risks with old PV modules. So each individual should be checked before going to a new plant. And if you have PV module prices of 10 cents per watt and below, as we've seen the last 2 years, now they're luckily rising again, but even that, it's just much more convenient, cheaper, higher efficiency. There's so many reasons at the moment from the economic side to buy new ones. Of course, the environmental side, the longer you use your product, the lower CO2 footprint, or the lower the environmental impacts beyond CO2, of course, are. The more energy you get out, you divide all the impacts by the electricity produced. But that's often not how you decide in the end. And if you cannot insure your new PV power plant, that's a showstopper already.
Yeah, I like to be the devil's advocate and ask these questions because I know that there are different values.
Yeah. Okay, I think we just passed our time, but thank you very much to our speakers, Sebastian, Rune, Burçak, and Ilham. And thanks to everyone who was here listening and asking questions. Yes, we hope to be in touch more and be able to follow up. But thank you.
Thank you very much for joining us.
Thank you.
Thank you very much for organizing this event. Thank you.